Okay, so what I would like to do in this lecture, which will be a short lecture, is talk about 4.6.1, which are basically properties of the binomial random variable. And what we're going to do is we're going to compute the expected value as well as the variance. I warn you that this computation is lengthy, so I'm going to take it slowly. Okay, so 4.6.1 properties of the binomial random variable. So let x be a random variable of type B and P. Recall that means that the probability density function is given by the sum of not the sum, but it's given by P of K equals n choose K, P to the K, 1 minus P to the n minus K. Oops. And here, K goes from 0, 1, all the way up to n. And all other values of P are 0. P of a million is 0 if n is less than a million. Okay, so I want to compute the expected value, first of all, as a preliminary computation of the random variable x to the k, where x is binomial of type NP. And so by definition, this is the same thing as the sum I goes from 0 to n of I to the power of k, n choose I, p to the I, 1 minus p to the n minus I, and we're summing from 0 to n. Okay, now when I equals 0, the first term of this sum is going to vanish. So you might as well write it as the sum I goes from 1 to n of the same thing, I to the k, and choose I, p to the I, 1 minus p to the n minus I. Okay, so now I'm going to appeal to the following identity that binomial coefficients satisfy. Suppose we take n, choose I, and multiply it by I. What do you get? Well, that's the same thing as I times n factorial over I factorial n minus I factorial. Now the I and the I factorial cancel to give you an I minus 1 factorial. And I could actually factor out from the n factorial a factor of n to make an n minus 1 factorial times n. So this is the same thing as n minus 1 factorial times n over I minus 1 factorial times n minus I factorial. Now, if you think about what this is, and if you group this, if you bring the n out, this is the same thing as n times n minus 1, choose I minus 1. You could easily check that. So that's the identity I want to use in all of this. So if I want to compute the expected value of x to the k, I can come down here and I can write that this is the same thing as the sum, and we're starting at 1 still. I goes from 1 to n of I to the power of k minus 1. I factor out an I from the I to the k. See, there's an I to the k. I factor out an I, and I group it with the n choose I, and then I use my identity to make an n, oops, an n times n minus I minus 1, oops, n minus 1, choose I minus 1, times p to the let me bring out a factor of p. So a p times the p to the I minus 1 times 1 minus p to the n minus I. Okay, and I'm going to pull out the n times the p. So that's going to be n times p times the sum. I goes from 1 to n of I to the k minus 1 times n minus 1, choose I minus 1, times p to the I minus 1 times 1 minus p to the n minus I. Okay, so we have that so far, and let me save. Okay, so I took the liberty of rewriting what I had on the previous slide on the top here. And now I'm going to set j equal to I minus 1. What do we get? So we get the expected value of x to the k is np. Okay, so if I starts at 1, j is starting at 0. So I'm reindexing, and it goes to n minus 1. And it becomes j plus 1, because I is j plus 1 to the k minus 1. N minus 1, choose j times p to the j times 1 minus p to the n minus I, but that's n minus j minus 1. Okay, and then you stare at this, and this is what happens if we let y be of type b of n minus 1 comma p. So then if we let y be any binomial random variable of type n minus 1 comma p, we notice that this sum is np times the expected value of something. What is it the expected value of? Well, if you stare at this, this is a j plus 1, and there's a k minus 1 here. It goes up to n minus 1. And if you stare at it for a while, you realize that what you have is the expected value of not y, but y plus 1. The y plus 1 occurs because there's a j plus 1 here to the k minus first power. So what we get is the following identity. The expected value of x to the k is np times the expected value of y plus 1 to the k minus 1. So this is almost like an inductive formula. And I'm just going to take low dimensions now of this formula. So we take k equals 1, we get the expected value of x, that's our random variable of type, binomial of type n comma p, is np times the expected value of y plus 1 to the 0th power, but that's the expected value of the constant 1, and that's going to be 1 so times np, so it's np. So we get that the expected value of the binomial random variable is n times p. Now let's compute the expected value of x squared. Well, if we use the formula, we get that's np, times the expected value of y plus 1, where y is of type n minus 1p. But what is the expected value of y plus 1? Well, it's np times the expected value of y plus 1 by one of the formulas we had on expected value. And so this is going to be the same thing as np times, well, we know from the previous calculation with x what the expected value of y is by just replacing n by n minus 1. It'll be n minus 1 times p plus 1. Okay, so that's the expected value of x squared. And so from that, we can actually compute the variance of x. The variance of x is the expected value of x squared minus the expected value of x squared on the outside. The squaring goes on the outside, and that's given by what we just did. So NP times n minus 1 p plus 1 minus NP quantities squared. Okay, so what do you get? Well, if you do the algebra, this expression becomes NP times 1 minus P. Okay, so that's the main calculation I wanted to do today. Let me summarize it on the next slide. Okay, so I've summarized what we've done so far with the expectation and the variance, and these are things you should try to commit to memory if possible. They'll come up again and again. Okay, the last thing I want to do today is make a computation which answers the following question. It turns so we could try to look at the graph of the binomial distribution, how it behaves. Okay, so it's a discrete random variable, but you have k equals 0 is the k-axis, and we can graph the the PMF, so the graph of the PMF, and ask what it looks like. And it turns out that it's going to look something like this. It's going to go up and then down, and we're going to show that right now. Okay, so here's the proposition. So P of K increases until it achieves its maximum, until K equals, and that maximum occurs at the greatest integer, the greatest integer n plus 1 times P. So I'm rounding it down. That's what this means. This is called the floor function. I'm rounding it down. So if n plus 1 times P is 1.5, I would get 1. Okay, so I'm going to give you a proof of that, and then afterwards it decreases. Okay, so let's give the proof. So it's enough. So let's figure out where. Let's consider when P of K over P of K minus 1 is less than 1. Well, that will be the same thing as when P of K is less than P of K minus 1. So this will tell us when it's decreasing if we can actually compute the left side. So what is P of K over P of K minus 1? Well, that's n choose K times P to the K times 1 minus P to the n minus K. That's the numerator, and the denominator is n choose K minus 1, P to the K minus 1 times 1 minus P to the n minus K plus 1. Okay, and what is that? Well, if you do the algebra, and this is just some algebra which you can do, I'm not going to do it. It's not hard. We get n minus K plus 1 times P over K times 1 minus P. That's what this expression is equal to. So, and actually, let's not consider the case, let's consider the opposite inequality. So let's consider this inequality, P of K greater than P of K over P of K minus 1. This is going to be where it's going to be, P is going to be an increasing function. So what do we get? So P of K is greater than P of K minus 1 if and only if this fraction is bigger than 1. So n minus K plus 1 times P over K times 1 minus P is bigger than 1. And that's by, this is just inequalities. It's if and only if n minus K plus 1 times P is bigger than K times 1 minus P. Just the usual just multiplying both sides by the denominator. And now you can easily subtract off, if you add both Kp to both sides, you'll see that this is if and only if K is strictly less than N plus 1 times P. But that's exactly what it means to be the floor of N plus 1 times P. It says that up until the greatest integer less than or equal to N plus 1 times P, you're going to have an increasing function, and otherwise it's going to be a decreasing function. So that is the proof of the proposition. And this section of the book only has one more thing. It has an application to elections, which you could read if you want to. I find it to be a bit long-winded, so I don't think I'm going to cover it. So that's all we need to know for section 4.6.1. Have a good one. Take care.